Welcome everyone to your first lesson in AP Calculus AB. Please make sure you are taking notes along with this video, either that you've downloaded the notes and printed them and you're following along there, or you're taking notes in your own notebook. We are going to ask you next class to submit a photo of your notes just to make sure that you're following along with us. So we're just going to go over a little introduction of calculus. And so calculus is really the study of rates of change. And so there are really two main questions that we'll ask: how fast something is changing or how much something is changing. That's kind of like the overarching idea of calculus. And so a very easy concept to think about is velocity, so how fast someone is moving. So over the summer, I visited my brother in Jersey City, New Jersey. The trip was about 700 miles, and it took me 10 hours to drive there. So what was my average velocity? So in order to think about average velocity, you may remember a formula from physics. It's change in distance over change in time. Now you can also talk about speed. We're going to specify that it's velocity here. We'll talk more about the difference later on. So the change in my distance was 700 miles. And my change in my time was 10 hours. And then if I divide those two, I would say my average velocity was 70 miles per hour. Now that seems maybe appropriate, but if you want to think about what the speed limit is, if the speed limit is 70 miles per hour and my average velocity was 70 miles per hour, what assumption could you make? So if my average velocity is 70 miles per hour, and you have to think at some times I had to accelerate up to that amount, I must have been going slower at some times, then maybe sometimes I was going over 70 miles per hour, which means I might have been speeding. And so obviously this is a hypothetical situation because I would never speed. I definitely followed the law. And so that's just a really easy way to calculate average velocity, change in distance over change in time. And really that's a type of average rate of change. We might call that average ROC, just for rate of change. So now to just a little background knowledge. So Galileo in the 1500s did some experiments from on top of the Leaning Tower of Pisa. And what he discovered is that distance that's traveled by a freely falling object is directly proportional to the square of the time it has been falling. So it doesn't matter how high up it was or how much the object weighed. No matter what, the distance the object has fallen would be given by this equation: S of t equals 16t squared. So S is your distance here, the distance the object has fallen. So let's use that formula in an example. So suppose the ball is dropped from the top story of the Burj Khalifa in Dubai, and it's 2,717 feet from the ground, and we want to find the velocity after 4 seconds. I'm going to underline this, so I want you to really think about using annotation in your notes so that you can pull out the key points. So notice that I put a box around this equation up here because I'm probably going to use it. And then what I'm trying to find is the velocity after 4 seconds. Now notice here it just said velocity. It didn't tell me what kind of velocity. And so if it's asking me for velocity at a certain time, that's talking about instantaneous velocity. So when you see instantaneous, that's at an instant. What we found up above was average velocity. So average velocity happens between two different times. Instantaneous velocity is at an instant. So could I still use that formula, change in distance over change in time, if I'm trying to find velocity at an instant? I actually wouldn't be able to if I did it just both at time equals 4, because my change in time would be 0. So if both of my times were at 4, then the change would be 0. And you should know, can't divide by 0. So instead, I'm going to just use times close to 4 and try to find the average velocity. Let's actually figure out what is our position at 4, how has our ball fallen? And so in order to do this, I'm just plugging 4 into 16t squared. And I get 256 feet. Now that I know what my position is at time t equals 4 at 4 seconds, I want to find my positions at some other times close to 4 seconds, but not quite 4 seconds. So we could start with 4.1. So in order to find that position, I'm going to be still evaluating 16t squared. And so what I'm going to use is Desmos. Hopefully you've used Desmos before, just to help me out. You could use your graphing calculator if you want as well. So what I'm going to type in over here is y equals 16t squared. Now I don't necessarily have to worry about the graph. I'm just going to make a table of values so I can plug in. And so I could hit that little gear and then click table. And I want to figure out what it is at 4.1. So that is 268.96. These are feet. I can put my units in the table, but I want to make sure I have them on my final answer. And then to find my average velocity, I can evaluate using the other point that I knew. So I knew S of 4 was 256. And so what I'm going to do, if I want to type a fraction, you can either do it in the middle or at the beginning. I think it's a little easier at the beginning. I'm going to hit the slash button like I'm dividing, and that automatically gives me a fraction in Desmos. So I'm going to put 268.96 minus 256, so that's my change in distance, divided by my change in time, which was 4.1 minus 4. And notice Desmos automatically calculates that for me, and I have 129.6. My units in the numerator were feet. My units in the denominator were seconds. So that's feet per second. I can do that same thing now. Let's get a little closer to 4, but still not quite 4. Let's do 4.01. So I see then at time 4.01, my position was 257.2816. I want you to use all those decimals for right now. We can round our final answers here. And then I can change my average velocity. I can just go down to the same formula and just change those numbers. Oops. All right, and I get 128.16 feet per second. And let's get a little closer to 4, not quite 4 still, 4.001. And I get 256.12802. And let's calculate our average velocity using that same value. Notice I'm only changing the first ones because the second point is always at 4. All right, and I get 128.2. And so that's just my average velocity as I'm getting closer and closer to 4. And so if I'm getting closer and closer to 4, you might notice that this value seems to be converging to something. So what that means is it's just approaching some value. What value do you think it's actually approaching? Hopefully you said it seems to be going towards 128. And so if we wanted to see that exactly, we could get closer and closer and closer. I could have tried 4.0001 or 4.00001. Just depends on how much work I want to do. And so this is just an approximation of that instantaneous velocity. Calculus, once we get to the real calculus part, will actually tell us how to find that exact answer. This is just an approximation. So what we're going to say is the instantaneous velocity is approximately 128 feet per second. So that big idea, really, let's talk about that in a more concrete way. really what we're saying is that average velocity over a very small time interval is very close to instantaneous velocity. And so what we really want to think about is getting infinitely close to some point. We'll never actually reach it, but we just want them to be infinitely close. I always like to think about, speaking about my brother again, when we would argue as kids and like your parents tell you like stop touching each other or something, and then like my brother would stick his finger like so close to my face but not actually touch it, right? So like he's not really breaking the rules, but he's still being annoying. That's what we're talking about here. So super close but not actually touching. So let's just do one more example like that. So we've got a roller coaster. It's designed to have its largest drop modeled by this equation. Again, let's go ahead and put a box around that equation. That's probably going to be important. So this distance equation is this cubic polynomial, where d of t is measured in feet and time t is measured in seconds. I always underline units as well. Sometimes on the AP test you get points just for your units, so you want to make sure to have those. So part A asks us for average velocity. And so remember, average velocity was change in position or change in distance over change in time. And so that would mean we would want our distance at 8 minus our distance at 2 over our time 8 and time 2. Now you could switch those around, the 2's and the 8's, but you just want to make sure they're both in the right order. So if you use 8 first, then you use 8 first in the denominator as well. Now I definitely don't want to do this by hand. I'm going to go back over to Desmos. And I actually have this typed in already. And so what you can do as well, besides just using that other table that I had made, I can add a table here. And x1 and then y1, instead of y1, I can say d of x1. So it's going to take my x's from the first column and put them in the second column. Just a different way to do it. And so I want to find d at 8 and d at 2. And so I have 671.36 minus 290.54 all over 6. And so I can type that in down here. Now what I could actually do, which is probably going to be easier for us, I could do d of 8 down here minus d of 2 all over 8 minus 2. Let's close that parenthesis up there. And it will automatically calculate it for me. So if I've already called that d up at the top, then it's just going to go ahead and calculate it. Now, we said d was measured in feet and time was seconds, so this is feet per second. All right, I want you to try part B on your own now. So open up Desmos if you haven't already and plug in that value. And you can pause this video and then come right back and you can check your answer. Okay, really go do it on your own if you're not already. All right, so to set this up, you want d of 6 minus d of 4 over 6 minus 4. Always show your setup. Again, on the AP test, a lot of times even just writing that setup might get you some partial credit. So you should have gotten 470.18 minus 373.16 all over 2. That's going to give us 48.51 feet per second. So those problems just straight up ask me for average velocity, so I just automatically know exactly what formula I need to do to calculate those. Part C, though, asks for instantaneous velocity. So instantaneous velocity at exactly 5 seconds. So make sure you underline that, exactly 5 seconds. Let's use this table of values to figure that out. So we want to think about points close to 5, but not exactly 5. So let's do 5.1, 5.01, 5.001, and 5.001. Now, we could have gone on the other side. We could have done like 4.9, 4.99, 4.999. It doesn't actually matter. We're just picking based on what we would like. And so then let's go ahead and type those values in. We want to give the distances, and then we'll also do the average velocities. And I just noticed I missed a 0 over here when I was writing mine. All right, so when I'm writing these down for right now, I'm just going to use 3 decimal places. So standard in AP Calculus is that we use 3 decimal places for when we're rounding. You can either round or truncate. So I could round that up since there's another 9 after, or I could just cut it off at 9. Either one is okay. And so what you might notice, these values seem to be getting closer to 414 point something. That's not really what we're looking at for average velocity though, that's distance. So we want to actually calculate average velocity. Now something fun that you can do, instead of having to retype that every time, we could actually put our formula up in this table. So I'm going to put some parentheses here because I want this up in the numerator. So right now I'm going to type in this formula over here into Desmos. I'm using the parentheses again because I want to make sure that's in the numerator. Now I'm going to have to use X because that's what I was using to begin with instead of T. And I can't see some of this. And notice, like, I'm not even worried about what's on the graph right now. I'm really just using Desmos for the table. All right, so let's write in our average velocities. 47.399, 46.714, 46.647, and 46.64. We could round it up to 1 if we want. And so what we're looking at is trying to see, is there some pattern? Is there some value that this seems to be converging to? So some value it's approaching. And it seems that maybe it's at about 46.64. It's, again, hard to know for sure without actually doing some calculus, which we'll get to later on. We're just estimating right now. So the instantaneous velocity is approximately 46.641. Again, it's going to be feet per second. All right, so next class, we're going to expand on this idea of getting closer and closer to some value and what that means, and we'll actually get to some of the calculus. This was just a preview.